Welcome to Loops and Loops, your go-to destination for all things microcontrollers. In the world of embedded systems and DIY electronics, microcontrollers serve as the brains behind countless innovative projects. Join us as we embark on a journey through the realm of microcontrollers, exploring their versatility, unraveling their functionalities, and empowering you to unleash your creativity. Whether you're a seasoned electronics enthusiast, a hobbyist looking to dive into the world of microcontrollers, or simply intrigued by the possibilities of embedded systems, you're in for an enlightening experience. So tighten your loops and let's dive into the fascinating world of microcontrollers together. A microcontroller is a small computer on a single integrated circuit chip that is designed to perform specific tasks and control electronic devices. It differs from a microprocessor in that it typically includes memory, input-output peripherals, and other features necessary for embedded applications, whereas a microprocessor is primarily focused on processing data and executing instructions. Essentially, while a microprocessor acts as the brain of a computer, a microcontroller serves as the brain of embedded systems and devices. The basic architecture of a microcontroller typically consists of a central processing unit, memory both volatile and non-volatile, input-output ports, GPIO pins, timers, counters, and communication interfaces such as UART, SPI, I2C. These components are integrated onto a single chip, allowing the microcontroller to execute instructions and interact with external devices. A microcontroller interacts with external peripherals and devices through its input-output ports, which can be configured to send and receive digital or analog signals. For example, digital pins can be used to control LEDs, switches, or motors, while analog pins can read values from sensors such as temperature sensors or light sensors. By connecting peripherals to the microcontroller's pins, developers can create custom electronic systems tailored to specific applications. Firmware is a type of software that is stored in the non-volatile memory of the microcontroller and is responsible for controlling its operation. It typically consists of a set of instructions and routines that define how the microcontroller interacts with peripherals, processes data, and performs tasks. Firmware is often written in low-level programming languages, such as C or assembly language, and is compiled into machine code that can be executed by the microcontroller. Programming a microcontroller involves writing code that defines the behavior and functionality of the device. This code is typically written in a high-level programming language, such as C or C++, then compiled into machine code that can be executed by the microcontroller. Programmers use development tools such as integrated development environments and compilers to write, debug, and upload code to the microcontroller. Microcontrollers commonly use programming languages such as C and C++ for development due to their efficiency, portability, and close to hardware capabilities. These languages allow developers to access low-level hardware features and write optimized code for embedded applications. A microcontroller executes instructions and performs tasks by fetching instructions from memory, decoding them, and executing them sequentially. It operates according to a program stored in its memory, which defines the sequence of operations and tasks. Microcontrollers can execute instructions at high speeds, allowing them to perform real-time tasks and respond to external events quickly. Interrupts are signals generated by external devices or internal peripherals that temporarily halt the execution of the microcontroller's main program to handle a specific event or task. Interrupts allow microcontrollers to respond to external events in a timely manner, such as reading data from a sensor or servicing a communication request, without delaying the execution of the main program. Microcontrollers find applications in a wide range of industries and devices, including consumer electronics, automotive systems, industrial automation, medical devices, and more. They are used to control and monitor electronic systems, process data, interface with sensors and actuators, and perform various tasks in embedded applications. Microcontrollers support the development of embedded systems by providing a compact, low-cost solution for controlling and monitoring electronic devices. They are used to create custom electronic systems and devices tailored to specific applications, such as home automation systems, wearable devices, and industrial control systems. In IoT devices, microcontrollers serve as the core processing unit that connects sensors, actuators, and communication modules to the internet. They collect data from sensors, process it, and transmit to cloud-based servers or other devices for analysis and action. Microcontrollers enable the development of smart, connected devices that can interact with the physical world and exchange data with other devices and systems. Sensors and actuators commonly interfaced with microcontrollers include temperature sensors, humidity sensors, motion sensors, pressure sensors, light sensors, motors, relays, and more. These peripherals allow microcontrollers to sense the environment, monitor conditions, and control physical devices in embedded applications. A microcontroller handles input and output operations by reading data from input peripherals, such as sensors and switches, and sending output signals to actuators and devices. Input operations involve reading digital or analog signals from external sensors or devices, while output operations involve controlling external devices by sending digital or analog signals to actuators such as motors, relays, or LEDs. Digital signals in microcontroller programming represent binary values such as 0, or 1 that can be used to encode information or control the state of a device. Analog signals, on the other hand, represent continuous quantities such as voltage or current and can be used to measure physical phenomena such as temperature, pressure, or light intensity. Microcontrollers support both digital and analog input-output operations, allowing them to interface with a wide range of sensors and devices in embedded applications. GPIO pins, which is general-purpose input-output pins, are versatile pins on a microcontroller that can be configured to either accept input signals from external devices or provide output signals to control external components. In microcontroller projects, GPIO pins serve as the interface between the microcontroller and the outside world, allowing it to interact with sensors, actuators, and other electronic devices. They can be used to read data from switches, buttons, or sensors, as well as to control LEDs, motors, relays, and other electronic components. Microcontrollers support communication with other devices and systems through various communication protocols, such as serial communication. Serial communication involves sending data one bit at a time over a single wire or pair of wires. This allows microcontrollers to exchange information with sensors, actuators, displays, and other microcontrollers or external devices. Serial communication protocols include Universal Asynchronous Receiver Transmitter, Serial Peripheral Interface, and I2C, which is Inter-Integrated Circuit, each with its own advantages and applications. Real-time applications require microcontrollers to respond to external events and process data within strict timing constraints. Microcontrollers handle real-time tasks by executing instructions sequentially and prioritizing critical tasks to ensure timely execution. Multitasking in microcontroller programming involves dividing the program into multiple tasks or threads that run concurrently, allowing the microcontroller to perform multiple tasks simultaneously. Real-time operating systems provide scheduling and task management capabilities for multitasking applications, ensuring that critical tasks are executed on time. Power management is crucial in microcontroller projects to conserve energy and prolong battery life. Microcontrollers manage power consumption by entering low-power sleep modes when idle or not actively processing data. Sleep modes reduce the microcontroller's clock frequency and disable unnecessary peripherals to minimize power usage while maintaining essential functionality. Optimizing power usage involves selecting appropriate sleep modes, adjusting clock frequencies, and minimizing the duration of active periods to maximize energy efficiency. Analog to digital conversion is the process of converting analog signals such as voltage or current into digital values that can be processed by a microcontroller. ADC is essential for interfacing with analog sensors and measuring physical quantities such as temperature, light intensity, or pressure. Sampling involves capturing analog signal samples at regular intervals, while quantization involves converting each sample into a digital value with a specific bit resolution. Analog sensors commonly used with microcontrollers include temperature sensors, light sensors, pressure sensors, and proximity sensors, among others. Microcontrollers interface with analog sensors and actuators through analog input-output pins. Analog input pins are used to read analog signals from sensors, while analog output pins are used to generate analog signals to control actuators such as motors or valves. Microcontrollers typically feature built-in analog to digital conversions and digital to analog converters to interface with analog sensors and actuators directly. Calibrating analog sensors involves measuring and adjusting sensor readings to ensure accuracy and consistency. This may involve compensating for sensor drift, non-linearities, or environmental factors that affect sensor performance. Calibration procedures vary depending on the type of sensor and its characteristics, but generally involve measuring known reference values and adjusting sensor readings accordingly to achieve accurate measurements. Digital to analog converters in microcontroller applications are responsible for converting digital signals into analog voltages or currents. This conversion is crucial when the microcontroller needs to interface with analog devices such as sensors, actuators, or audio equipment. Digital to analog converter enable microcontrollers to generate precise analog output signals that can control various analog components in a system. Microcontrollers utilize pulse width modulation techniques to generate analog-like signals using digital outputs. Pulse width modulation involves rapidly switching a digital signal on and off at varying duty cycles to simulate an analog voltage level. This technique is commonly used to control the speed of motors, the brightness of LEDs, or the power output to various devices. By adjusting the duty cycle of the pulse width modulation signal, microcontrollers can achieve precise control over analog components. Pulse width modulation is a technique that involves modulating the width of pulses in a digital signal to control the average power delivered to a load. In motor control applications, pulse width modulation is used to adjust the speed and direction of DC motors or the position of servo motors. Similarly, in LED lighting applications, pulse width modulation is used to control the brightness of LEDs by adjusting the duty cycle of the pulse width modulation signal. Microcontrollers play a vital role in robotics projects by providing the intelligence and control necessary to operate robotic systems. They handle tasks such as motor control, sensor interfacing, data processing, and decision-making, allowing robots to perform various tasks autonomously or under remote control. Interfacing motors and servos with a microcontroller involves connecting the control signals from the microcontroller to the input pins of the motor drivers or servo controllers. Motor drivers and servo controllers act as interfaces between the microcontroller and the motors, translating the control signals into appropriate voltage levels or pulse width modulation signals required to drive the motors or servos. Motor driver integrated circuits serve as interfaces between the microcontroller and the motors in robotics projects. These integrated circuits provide the necessary amplification and protection circuitry to drive motors efficiently and protect the microcontroller from voltage spikes or back electromotive force generated by the motors. For feedback control in robotic systems involves using sensors to measure the system's output and comparing it to a desired set point to adjust the system's inputs accordingly. Microcontrollers implement feedback control algorithms such as PID, which is proportional integral derivative control, to regulate the behavior of robotic systems, ensuring accurate and stable performance. PID control is a control loop feedback mechanism widely used in microcontroller programming to regulate processes and systems. It adjusts the control signal based on the error between the desired set point and the measured output, taking into account the proportional, integral, and derivative terms to achieve optimal control performance. PID control is commonly used in applications such as motor speed control, temperature regulation, and motion control. Autonomous systems controlled by microcontrollers include self-driving vehicles, autonomous drones, robotic arms, and smart appliances. These systems rely on microcontrollers to process sensor data, make decisions based on predefined algorithms or machine learning models, and execute actions to achieve their objectives without human intervention. Microcontrollers communicate with external devices and systems using various serial communication protocols such as universal asynchronous receiver transmitter, serial peripheral interface, and inter-integrated circuit. These protocols enable microcontrollers to exchange data with sensors, actuators, displays, memory modules, and other microcontrollers or external devices. Setting up universal asynchronous receiver transmitter communication with a microcontroller involves connecting the universal asynchronous receiver transmitter pins of the microcontroller to the corresponding pins of the universal asynchronous receiver transmitter-enabled device, such as a computer or a microcontroller. Universal asynchronous receiver transmitter communication uses two wires, one for transmitting data and one for receiving data, allowing bidirectional data transfer between devices. Serial communication protocols like serial peripheral interface and inter-integrated circuit facilitate communication between microcontrollers and peripheral devices such as sensors, memory modules, and displays. Serial peripheral interface is a synchronous serial communication protocol that uses multiple wires for communication, including separate lines for data transmission, reception, and clock synchronization. Inter-integrated circuit is a synchronous multi-master, multi-slave packet switch protocol commonly used for connecting low-speed peripherals to microcontrollers. Microcontrollers support wireless communication with other devices using technologies such as Bluetooth and Wi-Fi. Bluetooth enables short-range wireless communication between microcontrollers and smartphones, tablets, or other Bluetooth-enabled devices, allowing data exchange, remote control, and wireless networking. Wi-Fi provides high-speed wireless connectivity over longer distances, enabling microcontrollers to connect to local networks, the internet, and cloud services for remote monitoring, control, and data exchange. Internet of Things applications leverage microcontrollers with wireless connectivity to create smart interconnected devices and systems. Examples include smart home devices like thermostats, security cameras, and door locks that can be controlled remotely via smartphone apps. Industrial Internet of Things applications include monitoring systems for machinery, environmental sensors for agriculture, and asset tracking solutions in logistics. Microcontrollers handle data storage and retrieval using various storage options, including internal memory, external memory chips, and storage peripherals like SD cards or USB flash drives. These storage mediums allow microcontrollers to store program code, configuration settings, sensor data, and other information. Interfacing external memory with a microcontroller involves connecting the memory chip to the microcontroller's address, data, and control lines. The microcontroller communicates with the external memory using protocols such as serial peripheral interface or inter-integrated circuit to read from and write to memory addresses. Non-volatile memory options like electrically erasable programmable, read-only memory and flash memory provide storage solutions for microcontroller projects that require data retention even when power is removed. Electrically erasable programmable read-only memory allows for the storage of small amounts of data that need to be frequently updated, such as configuration settings or user preferences. Flash memory offers larger storage capacities. and is commonly used for storing program code and large data files. Microcontrollers support the development of data logging applications by providing the ability to capture, store, and analyze data from various sensors and inputs. Data logging involves recording measurements or events over time, which can be useful for monitoring system performance, analyzing trends, or troubleshooting issues. Data logging is the process of recording data from sensor inputs or other sources over time for analysis, monitoring, or archival purposes. In microcontroller-based systems, data logging applications capture data from sensors, store it in memory or external storage, and may display or transmit the data for further analysis or visualization. Environmental monitoring systems using microcontrollers include weather stations, air quality monitors, and pollution sensors. These systems use sensors to measure environmental parameters such as temperature, humidity, air quality, and radiation levels. Microcontrollers collect and process sensor data to provide real-time monitoring and analysis of environmental conditions. Microcontrollers handle user interface and interaction by interfacing with displays, buttons, touchscreens, and other input devices. Displays provide visual feedback to users, while input devices allow users to interact with the system by providing input commands or selections. Interfacing displays and input devices with a microcontroller involves connecting the display or input device to the microcontroller's GPIO. Pins or communication interfaces such as SPI or I2C. The microcontroller communicates with the display to update its content or receive input from the user. Touchscreens and keypads provide intuitive input interfaces for microcontroller projects, allowing users to interact with the system through touch gestures or button presses. Touchscreens offer versatile input options, while keypads provide tactile feedback and precise input control. Microcontrollers support the development of human-machine interfaces by enabling interactions between users and machines. HMIs allow users to monitor system status, adjust settings, and control operations through intuitive interfaces such as displays, buttons, and touchscreens. Graphical user interfaces with microcontrollers provide visual representations of system information, controls, and options. Graphical user interfaces enhance user experience by presenting information in a clear, organized manner and enabling interactive control through graphical elements such as buttons, sliders, and menus. Examples of embedded systems with user-friendly interfaces powered by microcontrollers include home automation controllers, industrial control panels, and medical devices. These systems feature intuitive interfaces that simplify user interaction and enhance usability for various applications. Microcontrollers handle timing and synchronization tasks using built-in timers and counters, which allow precise control over timing intervals, delays, and event scheduling. Timers and counters are hardware peripherals within microcontrollers that can generate precise time intervals, measure external signals, or count internal clock cycles. Using timers and counters in microcontroller programming involves configuring their settings, such as clock source, prescaler value, and operating mode, to achieve the desired timing or counting behavior. Microcontrollers use timers and counters for tasks such as generating PWM signals, measuring pulse durations, or triggering interrupts at specific intervals. Real-time clock modules in microcontroller-based systems serve to keep track of time even when the main system is powered off. They typically include a battery backup to ensure continuous timekeeping, allowing microcontrollers to maintain accurate time and date information for various applications such as logging events, scheduling tasks, or time-sensitive operations. Microcontrollers support the synchronization of multiple tasks and processes through various mechanisms, including interrupts, timers, and software synchronization techniques. By managing timing and scheduling, microcontrollers ensure that tasks are executed in a coordinated manner, enabling efficient operation and responsiveness in real-time systems. Interrupt-driven programming is a fundamental concept in microcontroller programming, where the processor responds to external events or signals by interrupting its current task to execute a specific interrupt service routine. Interrupts allow microcontrollers to handle time-critical events, such as sensor readings, user inputs, or communication requests, without delay, ensuring timely and responsive operation. Time-sensitive applications implemented with microcontrollers include real-time control systems, data acquisition systems, and communication protocols requiring precise timing. Microcontrollers provide mechanisms for accurate timing, synchronization, and event handling, enabling the development of applications that require precise timing or synchronization with external events. Microcontrollers handle environmental sensing and monitoring by interfacing with various sensors that measure parameters such as temperature, humidity, pressure, and air quality. These sensors provide real-time data about the surrounding environment, allowing microcontrollers to monitor environmental conditions and respond accordingly. Interfacing environmental sensors with a microcontroller involves connecting the sensor to the microcontroller's GPIO pins or communication interfaces such as I2C or SPI. The microcontroller reads sensor data and processes it to derive meaningful information about the environment, such as temperature trends, humidity levels, or air quality indices. Sensors like temperature, humidity, and pressure play essential roles in microcontroller projects by providing valuable data for environmental monitoring, climate control, and predictive analytics. Temperature sensors measure ambient temperature. Humidity sensors measure relative humidity, and pressure sensors measure atmospheric pressure, enabling microcontrollers to monitor and control environmental conditions effectively. Microcontrollers support the development of weather monitoring systems by integrating environmental sensors, data logging capabilities, and communication interfaces. Weather monitoring systems based on microcontrollers can collect real-time data on temperature, humidity, pressure, and other weather parameters, allowing users to track weather patterns, forecast changes, and make informed decisions. Remote sensing and telemetry with microcontrollers involve collecting data from remote locations using sensors and transmitting it wirelessly to a central monitoring station or data collection system. Microcontrollers equipped with wireless communication modules can establish connections with remote sensors, collect data, and transmit it over a network or communication link for analysis and monitoring. Examples of environmental monitoring projects using microcontrollers include weather stations, air quality monitors, soil moisture sensors, and water quality analyzers. These projects leverage microcontrollers' capabilities to interface with sensors, process data, and communicate information to users or central monitoring systems for environmental assessment and management. Microcontrollers handle signal processing and analysis tasks by executing algorithms that manipulate and analyze digital signals in real time. Digital signal processing algorithms implemented on microcontrollers enable applications such as filtering, noise reduction, signal enhancement, and feature extraction for various signal processing tasks. Implementing DSP algorithms with a microcontroller involves writing software code to perform mathematical operations on digital signal samples. Microcontrollers execute these algorithms in real time, processing input signals from sensors, communication interfaces, or external sources to extract useful information or perform specific tasks required by the application. Microcontrollers play a significant role in audio processing and synthesis by generating, processing, and analyzing audio signals in real time. They can generate audio waveforms, apply digital effects, perform audio mixing, and analyze audio content for tasks such as speech recognition, music synthesis, or sound processing in various applications. Speech recognition systems using microcontrollers enable voice-controlled interfaces, smart assistants, and voice-activated devices. Microcontrollers process audio signals captured by microphones, apply signal processing techniques to extract features or patterns, and use machine learning algorithms to recognize spoken words or commands, enabling hands-free operation and interaction with devices. Fast Fourier transform analysis in microcontroller programming is a mathematical technique used to transform time domain signals into frequency domain representations. Microcontrollers implement FFT algorithms to analyze and process signals in the frequency domain, enabling tasks such as spectrum analysis, frequency detection, and audio equalization in real-time applications. Signal processing applications implemented with microcontrollers include audio processing, speech recognition, image processing, biomedical signal analysis, and vibration analysis. Microcontrollers process analog or digital signals from sensors or external sources to extract useful information, detect patterns, or perform specific tasks required by the application. Microcontrollers handle encryption and secure communication by implementing cryptographic algorithms and communication protocols to protect sensitive data. They encrypt data using encryption algorithms and establish secure communication channels using protocols to ensure data confidentiality, integrity, and authenticity. Setting up certificates on a microcontroller involves generating or obtaining digital certificates and configuring the microcontroller's communication stack to use these certificates for secure communication. The process may vary depending on the microcontroller platform and the communication library used. Microcontrollers play a crucial role in secure communication and data protection by implementing encryption, authentication, and secure communication protocols to safeguard sensitive information from unauthorized access, interception, or tampering. Microcontrollers support the development of projects involving cryptography by providing hardware-accelerated cryptographic operations, cryptographic libraries, and communication interfaces for secure data exchange. Cryptographic techniques implemented with microcontrollers include encryption, hashing digital signatures, and key management. Advanced encryption standard with microcontrollers involves using advanced encryption standard algorithm implementations to encrypt and decrypt data securely. Microcontrollers execute AES encryption algorithms efficiently, making them suitable for applications requiring data encryption, such as secure communication, data storage, and authentication. Secure communication applications using microcontrollers include secure messaging, encrypted data transfer, secure access control systems, and encrypted file storage. Microcontrollers establish secure communication channels using encryption algorithms and protocols to protect sensitive data exchanged between devices or systems. Microcontrollers handle power management and energy efficiency by implementing power-saving techniques, low power modes, and energy-efficient hardware designs to minimize power consumption and extend battery life. They optimize power usage by selectively powering down unused peripherals, reducing clock frequencies, or entering low-power sleep modes when idle. Optimizing power consumption in microcontroller-based systems involves designing hardware circuits and writing software code to minimize power usage during operation. Techniques such as duty cycling, voltage scaling, and sleep mode optimization are used to reduce power consumption in microcontroller projects. Sleep modes in microcontroller projects conserve power by putting the microcontroller into a low power state when idle or inactive. Sleep modes disable unnecessary peripherals and reduce the microcontroller's clock frequency to minimize power consumption while maintaining essential functions such as wake-up timers or interrupt detection. Microcontrollers support the development of battery-powered devices by implementing power-efficient designs, low-power sleep modes, and energy-saving algorithms to maximize battery life. They manage power consumption to ensure optimal performance while preserving battery capacity for extended operation. Energy harvesting is the process of capturing and converting ambient energy from sources such as light, heat, or motion into electrical energy to power microcontroller-based systems. Microcontrollers interface with energy harvesting modules to harvest energy from the environment and regulate power delivery to the system. Low-power applications implemented with microcontrollers include wearable devices, Internet of Things sensors, remote monitoring systems, and battery-powered gadgets. These applications leverage microcontrollers' power-saving features and efficient operation to achieve long battery life and reliable performance in low-power environment. Microcontrollers handle data acquisition and processing by interfacing with sensors, acquiring sensor data, processing it in real time, and taking appropriate actions based on the processed information. They read analog or digital signals from sensors, convert them into digital format, and execute algorithms to analyze and respond to the acquired data. Analog to digital converters in microcontroller projects convert analog signals from sensors or external sources into digital data that the microcontroller can process. This conversion allows microcontrollers to read and interpret real-world signals such as temperature, light, or pressure, enabling a wide range of applications from environmental monitoring to industrial automation. Microcontrollers support the development of data logging projects by providing interfaces for storing data in onboard memory or external storage devices. Data logging involves capturing and recording sensor data over time, allowing users to analyze trends, monitor system performance, or track environmental conditions. Microcontrollers can periodically sample sensor data and store it in a structured format for later analysis or retrieval. Filtering and pre-processing sensor data with microcontrollers involves applying algorithms or techniques to enhance the quality of raw sensor measurements. This process may include removing noise, smoothing fluctuations, or scaling sensor readings to improve accuracy and reliability. By pre-processing sensor data, microcontrollers ensure that the information used for decision-making or analysis is reliable and consistent. To data acquisition and processing applications, using microcontrollers include environmental monitoring, health tracking, smart agriculture, and industrial control systems. Microcontrollers gather data from sensors, process it in real time, or store it for later analysis, and take appropriate actions based on the processed information. These applications leverage microcontrollers' versatility and computational capabilities to address diverse data acquisition needs. Microcontrollers handle wireless communication and IoT by integrating wireless modules or communication interfaces such as Wi-Fi, Bluetooth, or cellular connectivity. These modules allow microcontrollers to exchange data with other devices or connect to the internet, enabling IoT applications such as remote monitoring, smart home automation, or asset tracking. Setting up Wi-Fi or Bluetooth communication with a microcontroller involves configuring communication parameters, establishing connections with other devices, and implementing protocols for data exchange. Microcontrollers communicate wirelessly using standardized protocols and libraries, simplifying the development of wireless-enabled projects. Microcontrollers support the development of cloud-connected devices by providing interfaces for interacting with cloud platforms and services. These devices can upload sensor data, receive commands or updates from the cloud, and participate in IoT ecosystems, enabling scalable and connected solutions. Edge computing with microcontrollers involves processing data locally on the device instead of relying solely on cloud resources. By performing data analysis, decision-making, or pre-processing at the edge, microcontrollers reduce latency, conserve bandwidth, and enhance privacy in IoT applications. Examples of IoT applications using microcontrollers for data transmission include smart thermostats, wearable fitness trackers, environmental sensors, and smart lighting systems. These devices collect sensor data, communicate with other devices or cloud services, and provide insights or control based on the received information. Microcontrollers handle motor control and robotics by generating control signals to drive motors or servos based on input commands or sensor feedback. Interfacing motors and servos with a microcontroller involves connecting them to dedicated output pins and implementing control algorithms to regulate speed, position, or torque. Motor driver integrated circuits in robotic projects with microcontrollers provide integrated solutions for driving motors efficiently and safely. These integrated circuits handle tasks such as current regulation, voltage amplification, and motor direction control, simplifying motor interfacing and control in robotic applications. Microcontrollers support the development of autonomous systems by executing control algorithms that enable devices to operate independently, make decisions, and adapt to changing conditions. Examples include autonomous drones, robotic vacuum cleaners, self-balancing robots, and autonomous vehicles. Proportional integral derivative control with microcontrollers involves implementing a control algorithm that adjusts control signals based on the error between desired and actual system states. By continuously monitoring error signals and applying corrective actions, microcontrollers achieve precise control and stability in various applications, including robotics, process control, and automation. In robotics applications, microcontrollers play a crucial role in controlling the motion of robots. They receive input from sensors, process it, and generate output signals to drive motors or actuators. Examples include robotic arms used in manufacturing, autonomous drones for aerial surveillance, and mobile robots for navigation in warehouses or hospitals. Microcontrollers handle user interface and interaction by interfacing with various input and output devices. These devices include displays such as LCD screens or OLED panels for visual feedback, as well as input devices like buttons, switches, or touchscreens for user input. Interfacing displays and input devices with a microcontroller involves connecting them to the microcontroller's pins or ports and implementing communication protocols to exchange data. For example, a display may use a serial interface like SPI or I2C, while input devices may be connected via digital or analog pins. Touchscreens and keypads provide intuitive interfaces for users to interact with microcontroller-based systems. Touchscreens allow users to input commands or interact with graphical user interfaces through touch gestures, while keypads offer tactile buttons for inputting alphanumeric or numeric data. Microcontrollers support the development of touchscreen interfaces by providing interfaces for reading touch input from capacitive or resistive touch panels. Capacitive touch sensing, in particular, detects changes in capacitance caused by touching the screen, enabling precise and responsive touch input. User interface applications using microcontrollers include smartphones, tablets, industrial control panels, and home automation systems. These applications provide users with intuitive interfaces for controlling devices, accessing information, or interacting with digital content. Real-time data acquisition and processing with microcontrollers involve capturing sensor data and processing it in a timely manner to meet strict timing requirements. Microcontrollers use interrupts, which are signals that temporarily halt the main program, to handle time-sensitive tasks, such as reading sensor data or generating output signals. Real-time operating systems provide microcontrollers with scheduling and prioritization capabilities to ensure that critical tasks are executed on time. Real-time operating systems manages task execution, interrupt handling, and resource allocation, enabling microcontrollers to handle time-sensitive applications effectively. Microcontrollers support the development of data logging applications by providing interfaces for storing and retrieving data from internal or external memory devices. Data logging involves capturing sensor data over time and storing it for later analysis or archival purposes. Data buffering and streaming with microcontrollers involve storing incoming data temporarily in memory buffers before processing or transmitting it. This technique helps manage data flow rates, especially in applications where data arrives continuously or intermittently. Examples of real-time data acquisition and processing applications include monitoring vital signs in medical devices, controlling industrial processes, managing inventory and logistics systems, and processing sensor data in automotive systems. Power management and energy efficiency are critical considerations in battery-powered microcontroller projects to extend battery life and optimize performance. Microcontrollers use techniques such as low power modes, sleep modes, and dynamic voltage scaling to minimize power consumption while maintaining functionality. Low power modes in microcontroller-based systems are essential for extending battery life by reducing power consumption when the device is idle or not actively processing data. These modes allow the microcontroller to enter sleep states where it consumes minimal power while still maintaining critical functionality. By strategically transitioning between low power modes and active states, developers can optimize energy usage and prolong battery life in portable or battery-powered devices. Microcontrollers support the development of energy-efficient applications by providing features such as low power modes, sleep timers, and power management peripherals. Developers can leverage these capabilities to design systems that minimize power consumption during operation and maximize energy efficiency across various use cases and environmental conditions. Energy harvesting is a technique used to capture and convert ambient energy from sources such as light, heat, vibration, or motion into electrical energy to power microcontroller-based systems. Microcontrollers equipped with energy harvesting circuits can harvest energy from their surroundings and use it to supplement or replace battery power, enabling sustainable and self-sufficient operation in remote or off-grid locations. Low-power applications implemented with microcontrollers include wireless sensor networks, wearable devices, remote monitoring systems, and battery-operated sensors. These applications leverage power-efficient design principles and low-power features of microcontrollers to achieve long battery life or operate in energy-constrained environments. Microcontrollers handle communication with other devices and systems through various serial communication interfaces. Developers can configure these interfaces to establish connections with external devices, sensors, actuators, or other microcontrollers, enabling data exchange and system integration. Communication protocols like Modbus and Controller Area Network are widely used in industrial applications for inter-device communication, data exchange, and control in industrial automation, manufacturing, and process control systems. Microcontrollers support these protocols through dedicated hardware peripherals or software libraries, facilitating seamless integration into industrial environments. Microcontrollers support wireless communication protocols, such as long-range and Zigbee for long-range and low-power wireless networking in IoT applications. These protocols enable microcontroller-based devices to communicate wirelessly with each other, access points or gateways, extending the range and flexibility of IoT deployments. Examples of IoT applications using microcontrollers for wireless data transmission include smart home systems, environmental monitoring networks, asset tracking solutions, and agricultural monitoring systems. These applications rely on microcontrollers to collect sensor data, communicate wirelessly, and transmit data to centralized servers or cloud platforms for analysis and decision-making. Microcontrollers handle data storage and retrieval by interfacing with external memory devices, such as electrically erasable programmable read-only memory and flash memory. These memory options provide non-volatile storage for program code, configuration data, or user-generated content, enabling persistent storage of critical information in microcontroller-based systems. Non-volatile memory options like electrically erasable programmable ROM and Flash play a vital role in microcontroller projects by providing reliable, low-cost, and rewritable storage solutions for storing firmware, configuration parameters, and user data. These memory options retain data even when power is removed, making them suitable for applications requiring persistent storage. Microcontrollers support the development of data logging and storage applications by providing interfaces for reading from and writing to external memory devices. Developers can implement data logging functionality to record sensor measurements, system events, or user interactions over time, enabling analysis, monitoring, and troubleshooting of microcontroller-based systems. We're leveling and error correction. Techniques used in flash memory to improve reliability and longevity by distributing write and erase cycles evenly across memory cells and detecting and correcting errors caused by wear or data corruption. These techniques ensure consistent performance and data integrity in data logging and storage applications using flash memory. Data storage and retrieval applications using microcontrollers include systems for logging sensor data, storing user settings, and maintaining device configuration parameters. For example, a weather station may use a microcontroller to log temperature, humidity, and atmospheric pressure readings to an external electrically erasable programmable read-only memory chip, allowing users to retrieve historical weather data for analysis. Similarly, a home automation system might store user preferences and schedule information in flash memory for later retrieval and use. Microcontrollers handle signal processing and analysis by executing digital signal processing algorithms to analyze and manipulate incoming data from sensors or other sources. To implement digital filters and algorithms, developers write code that performs mathematical operations on data samples, such as averaging, smoothing, or noise reduction. These algorithms are often implemented using programming languages like C or C++, leveraging the microcontroller's computational capabilities to process signals in real time. DSP libraries provide pre-written code modules for performing common signal processing tasks, such as filtering, convolution, or spectral analysis on microcontrollers. These libraries simplify the development process by offering optimized and tested implementations of DSP algorithms, allowing developers to focus on higher-level application logic rather than low-level algorithm implementation details. Microcontrollers support the development of projects involving audio processing by providing interfaces for connecting to audio input and output devices, such as microphones, speakers, or audio codecs. Developers can use microcontrollers to implement audio processing algorithms for tasks like noise cancellation, equalization, or audio compression. Signal processing applications using microcontrollers include systems for audio processing, biomedical signal analysis, vibration monitoring, and condition monitoring in industrial machinery. These applications leverage the microcontroller's computational capabilities to process signals in real time and extract meaningful information for analysis or control purposes. Microcontrollers handle encryption and secure communication by implementing cryptographic algorithms to encrypt and decrypt data and secure communication channels. Developers can use microcontrollers to implement encryption algorithms such as Advanced Encryption Standard or Reivers-Schmier-Edelman to protect sensitive data and ensure secure communication between devices. To implement encryption algorithms, with a microcontroller, developers write code that performs cryptographic operations such as key generation, encryption, and decryption using libraries or custom implementations. These algorithms use mathematical principles to encode data in a way that can only be decoded with the correct decryption key, providing confidentiality and integrity protection. Cryptographic libraries provide pre-written code modules for implementing cryptographic algorithms on microcontrollers. These libraries offer optimized and tested implementations of encryption and decryption algorithms, making it easier for developers to integrate secure communication features into their projects. Microcontrollers support the development of secure IoT devices by providing features such as secure boot mechanisms, cryptographic accelerators, and hardware security modules. Secure boot ensures that only authenticated and trusted firmware is loaded during device startup, protecting against unauthorized firmware modification or tampering. Firmware update mechanisms allow devices to securely update their firmware over the air, ensuring the integrity and authenticity of firmware updates. Examples of secure communication applications using microcontrollers include encrypted messaging systems, secure data transfer protocols, and authenticated communication channels. These applications use cryptographic algorithms and secure communication protocols to protect data privacy, integrity, and authenticity in IoT deployments. Low power modes in microcontroller-based systems are essential for extending battery life by minimizing power consumption during periods of inactivity or low processing demand. When a microcontroller enters a low power mode, it reduces its clock frequency, disables unnecessary peripherals, and enters a sleep state to conserve energy. By utilizing low power modes strategically, developers can significantly extend the battery life of devices powered by microcontrollers, making them suitable for energy-efficient applications such as battery-operated sensors, wearable devices, and IoT endpoints. Microcontrollers support the development of energy-efficient applications by offering features like low power modes, efficient clock management, and hardware peripherals optimized for power efficiency. Developers can leverage these features to design systems that minimize power consumption while still meeting performance requirements. Techniques such as duty cycling, where the microcontroller operates intermittently to perform tasks before returning to a low power state, further contribute to energy efficiency. Energy harvesting involves capturing and converting ambient energy from the environment, such as solar radiation, vibration, or thermal gradients, into electrical energy to power microcontroller-based systems. Microcontrollers can interface with energy harvesting modules, such as solar panels or piezoelectric generators, to harvest energy in charged batteries, or capacitors for powering devices in remote or off-grid locations. Energy harvesting enables sustainable and self-sufficient operation of microcontroller-based systems without relying on external power sources. Low-power applications implemented with microcontrollers include wearable fitness trackers, wireless sensor nodes for environmental monitoring, and remote control systems for home automation. These applications utilize efficient power management techniques and low-power peripherals to minimize energy consumption, enabling prolonged battery life and operation in energy-constrained environments. Communication protocols like Modbus and controller area network play vital roles in industrial applications by facilitating communication between microcontrollers, sensors, actuators, and supervisory control systems. Modbus is a widely used serial communication protocol for industrial automation, while CAN is prevalent in automotive and manufacturing environments for high-speed, reliable communication between distributed devices. Microcontrollers support the development of projects involving wireless communication by integrating wireless modules like Wi-Fi, Bluetooth, long range, or Zigbee. These wireless modules enable microcontrollers to establish wireless connections with other devices, access points or network gateways for data transmission and remote control. Long range and Zigbee are long power, long range wireless communication technologies suitable for IoT applications requiring extended range and battery life. Examples of IoT applications using microcontrollers for wireless data transmission include environmental monitoring systems, smart agriculture solutions, and asset tracking systems. These applications leverage microcontrollers equipped with wireless connectivity to collect sensor data, communicate with centralized servers or cloud platforms, and enable remote monitoring and control over the internet. Microcontrollers handle data storage and retrieval by interfacing with external memory devices such as electrically erasable programmable ROM and flash memory. Developers can use these non-volatile memory options to store configuration settings, application data, or firmware updates persistently. Electrically erasable programmable ROM provides byte-level read and write operations, while flash memory offers larger storage capacities and faster access times, making them suitable for data logging and storage applications. In data logging and storage applications, microcontrollers continuously collect and store sensor data, event logs, or system parameters to external memory devices for later retrieval and analysis. By logging data to non-volatile memory, developers can ensure data integrity and preserve information across power cycles or system resets, enabling applications such as environmental monitoring, industrial process control, and fault diagnostics. Where leveling error correction are techniques used in flash memory management to extend its lifespan and ensure data reliability. Where leveling algorithms distribute write and erase operations evenly across flash memory blocks, preventing premature wear out of specific memory regions and prolonging the overall lifespan of the memory device. Error correction codes detect and correct data errors that may occur due to program or erase cycles, ensuring data integrity and reliability in flash memory-based storage systems. Data storage and retrieval applications using microcontrollers encompass various scenarios where data needs to be stored persistently and accessed as required. For instance, a microcontroller might store sensor readings in non-volatile memory for later analysis, logging environmental conditions over time for monitoring purposes. In another example, a microcontroller-based system could log user interactions or configuration settings to maintain state across power cycles or device resets. These applications often leverage external memory devices, like electrically erasable programmable ROM or flash memory for reliable data storage, enabling seamless retrieval of information when needed. Signal processing and analysis with microcontrollers involve manipulating and interpreting signals acquired from sensors or external sources. Microcontrollers can implement digital filters and algorithms to pre-process sensor data, remove noise, or extract relevant information for further analysis. For example, in a temperature monitoring system, a microcontroller might apply a low-pass filter to smooth out fluctuations in temperature readings caused by sensor noise, providing more accurate data for analysis. Implementing digital filters and algorithms with a microcontroller typically involves writing software code that defines the mathematical operations required to process signals. Developers write algorithms in programming languages like C or C++, leveraging built-in functions and libraries provided by the microcontroller's development environment. By configuring the microcontroller's hardware, peripherals, and registers, developers can efficiently execute signal processing tasks in real time, ensuring timely and accurate data analysis. DSP libraries play a crucial role in microcontroller projects by providing pre-written functions and algorithms optimized for digital signal processing tasks. These libraries offer a range of functionalities, including filtering, convolution, Fourier transforms, and spectral analysis, simplifying the development of signal processing applications. By leveraging DSP libraries, developers can accelerate project development, reduce code complexity, and achieve optimal performance on resource-constrained microcontroller platforms. Microcontrollers support the development of projects involving audio processing by interfacing with audio input and output devices such as microphones, speakers, and audio codecs. In audio processing applications, microcontrollers can capture audio signals, Apply digital signal processing techniques for tasks like noise cancellation or equalization, and output processed audio signals to speakers or recording devices. Examples of audio processing applications include voice recognition systems, music synthesis, and audio effects processing. And fast Fourier transform analysis is a mathematical technique used in microcontroller programming to analyze the frequency content of signals. By performing FFT analysis on sampled data, microcontrollers can decompose complex signals into their constituent frequency components, enabling tasks like spectrum analysis, filtering, or modulation detection. In audio processing applications, FFT analysis is commonly used for tasks like spectrum visualization, pitch detection, or sound classification. Signal processing applications using microcontrollers span various domains, including audio processing, sensor data analysis, and communication systems. Examples include speech recognition systems, biomedical signal processing for healthcare monitoring, radar signal processing for object detection, and modulation to modulation techniques for wireless communication systems. In each case, microcontrollers perform real-time signal processing tasks to extract meaningful information from input signals, enabling advanced functionality and intelligent decision-making. Microcontrollers handle encryption and secure communication by implementing cryptographic algorithms to protect sensitive data and establish secure communication channels with other devices. To implement encryption algorithms, developers write software code that performs cryptographic operations such as encryption, decryption, key generation, and authentication. These algorithms leverage cryptographic primitives like block ciphers, hash functions, and public key cryptography to ensure data confidentiality, integrity, and authenticity. Cryptographic libraries provide a collection of functions and algorithms for implementing encryption, decryption, and secure communication protocols on microcontroller platforms. These libraries offer standardized implementations of cryptographic algorithms, ensuring compliance with security best practices and industry standards. By utilizing cryptographic libraries, developers can simplify the implementation of secure communication features in their microcontroller projects while benefiting from optimized and tested cryptographic routines. Microcontrollers support the development of secure IoT devices by implementing security features such as secure boot, secure firmware updates, and cryptographic protocols for data encryption and authentication. Secure boot mechanisms ensure that only trusted firmware images are loaded and executed on the microcontroller, guarding against unauthorized modifications or tampering. Secure firmware update mechanisms enable secure over-the-air updates, allowing devices to receive and install firmware updates securely even in untrusted network environments. Examples of secure communication applications using microcontrollers include secure IoT gateways, encrypted sensor networks, and authenticated data exchanges between connected devices. In these applications, microcontrollers establish secure communication channels using protocols like transport layer security or datagram transport layer security, encrypting data in transit and authenticating communication endpoints to prevent unauthorized access or data tampering. Microcontrollers handle power management and energy efficiency by implementing various techniques to minimize power consumption in battery-powered applications. Developers optimize power consumption by employing low power modes, duty cycling, and intelligent sleep. Wake strategies to reduce energy consumption during idle periods. Additionally, microcontrollers incorporate hardware features like power gating, clock gating, and voltage scaling to dynamically adjust power usage based on processing demands, further enhancing energy efficiency. Optimizing power consumption in battery-powered microcontroller. Projects involves carefully managing the microcontroller's operational states and peripheral usage to minimize energy waste. Developers analyze power consumption profiles, identify power-hungry components or functions, and implement power-saving techniques such as disabling unused peripherals, reducing clock frequencies, or entering low-power sleep modes when the system is idle. By optimizing power consumption, developers can extend battery life and improve the overall energy efficiency of microcontroller-based devices. Low power modes are essential for extending the battery life of microcontroller-based systems. These modes allow microcontrollers to enter low energy states when idle or inactive, conserving power consumption. By minimizing power usage during periods of inactivity, low power modes help prolong the operating time of battery-powered devices, making them more energy efficient and cost-effective in the long run. Microcontrollers support the development of energy-efficient applications through various features and techniques aimed at reducing power consumption. Developers can optimize code execution, manage peripheral usage, and employ sleep modes to minimize energy consumption during operation. By adopting energy-efficient design practices and leveraging hardware features like low-power peripherals, developers can create applications that consume less power without compromising performance or functionality. Energy harvesting involves capturing and converting ambient energy from the environment into electrical power to supplement or replace batteries in microcontroller-based systems. This harvested energy can come from sources such as solar radiation, vibration, thermal gradients, or RF signals. Microcontrollers can integrate energy harvesting circuits to capture and store energy efficiently, enabling self-sustaining or energy-neutral operation in certain applications. Examples of low-power applications implemented with microcontrollers include battery-operated sensors, wearable devices, and remote monitoring systems. These applications leverage low-power microcontrollers, efficient power management techniques, and optimized firmware to minimize energy consumption and extend battery life. By operating in low-power modes and implementing power-saving features, microcontroller-based systems can achieve long-term operation without frequent battery replacement. Setting up UART SPI or I2C communication with a microcontroller involves configuring the microcontroller's hardware peripherals, specifying communication parameters such as baud rates, data formats, and clock frequencies, and implementing software routines to send and receive data over the chosen interface. By establishing serial communication links, microcontrollers can exchange data with a wide range of external devices, enabling seamless integration into larger systems. Communication protocols like Modbus and Controller Area Network play a crucial role in industrial applications by facilitating data exchange between microcontrollers and industrial equipment sensors or control systems. Modbus is a widely used serial communication protocol for connecting industrial devices, while CAN is a robust fault-tolerant protocol commonly used in automotive and industrial automation applications. Microcontrollers support the development of projects involving wireless communication by integrating wireless transceivers or modules and implementing wireless communication protocols such as LoRa and Zigbee. Long range is a low power. Long-range wireless communication technology is suitable for IoT applications, requiring extended communication range and low power consumption. Zigbee is a low-power mesh networking protocol commonly used in home automation, smart energy, and industrial control applications. Examples of IoT applications using microcontrollers for wireless data transmission include smart home devices, environmental monitoring systems, asset tracking solutions, and industrial automation systems. In these applications, microcontrollers collect sensor data, process it locally, and transmit wirelessly to centralized servers, cloud platforms, or other connected devices, enabling real-time monitoring, control, and analysis. Microcontrollers handle data storage and retrieval by interfacing with external memory devices, such as electrically erasable programmable ROM and flash memory. Electrically erasable programmable ROM provides non-volatile storage for small amounts of data that need to be retained across power cycles or device resets, while flash memory offers larger storage capacity and faster access times, making it suitable for program storage and data logging applications. Interfacing external memory devices with a microcontroller involves connecting the memory device to the microcontroller's memory bus, configuring the microcontroller's memory controller, and implementing software routines to read from and write to the memory device. By utilizing external memory, microcontrollers can expand their storage capacity and support data-intensive applications such as data logging, firmware updates, and multimedia playback. Non-volatile memory options like electrically erasable programmable, ROM, and flash play a crucial role in microcontroller projects by providing persistent storage for program code, configuration settings, user data, and logging information. Electrically erasable programmable ROM is commonly used for storing small amounts of critical data that require frequent updates, while flash memory is ideal for storing program code, firmware updates, and large data sets that need to be accessed quickly and reliably. Microcontrollers support the development of data logging and storage applications by providing interfaces to external memory devices, implementing file systems and data structures for organizing and accessing stored data, and offering features like wear leveling and error correction to ensure data integrity and reliability. By logging data to external memory, microcontrollers can capture and store sensor readings, system logs, or user interactions for analysis, monitoring, or archival purposes. Wear leveling and error correction are techniques used in flash memory management to prolong the lifespan and reliability of flash-based storage devices. Wear leveling distributes write and erase operations evenly across the memory cells to prevent premature wear out of individual cells, extending the overall lifespan of the flash memory. Error correction algorithms detect and correct data errors caused by bit flips or other forms of corruption, ensuring data integrity and reliability during read and write operations. Data storage and retrieval applications using microcontrollers include systems for logging sensor data, storing configuration settings, recording user inputs, and managing databases. For example, a weather station built with a microcontroller might log temperature, humidity, and air pressure readings to internal memory, allowing users to retrieve historical data for analysis. Similarly, a smart home device could store user preferences and device settings in non-volatile memory, ensuring they persist across power cycles. Microcontrollers handle signal processing and analysis by executing algorithms to manipulate and interpret analog signals captured from sensors or generated by external devices. For instance, a microcontroller might filter noisy sensor data using digital filters to extract meaningful information, such as detecting peaks or trends in sensor readings. Signal processing algorithms implemented on microcontrollers enable applications like audio filtering, image processing, and vibration analysis. Implementing digital filters and algorithms with a microcontroller involves writing software routines to perform mathematical operations on sampled data. Developers define filter characteristics such as cutoff frequency, filter order, and response type. Then implement algorithms like finite impulse response or infinite impulse response filters to process the data. By applying these algorithms, microcontrollers can remove noise, smooth signals, or extract specific features from raw data. DSP libraries provide pre-written software routines and functions optimized for digital signal processing tasks on microcontrollers. These libraries offer a range of signal processing algorithms, including filtering, convolution, Fourier transforms, and spectral analysis. By leveraging DSP libraries, developers can accelerate development, reduce code complexity, and achieve higher performance in signal processing applications on microcontrollers. Microcontrollers support projects involving audio processing by executing algorithms to capture, process, and output audio signals in real time. For example, microcontrollers can sample audio inputs from microphones, apply digital effects or filters, and output processed audio to speakers or headphones. Audio processing applications include music synthesis, speech recognition, noise cancellation, and audio equalization. FFT analysis is a mathematical technique used to decompose a time domain signal into its frequency components. In microcontroller programming, FFT algorithms are applied to digitize signals to analyze their frequency content and identify dominant frequencies or spectral characteristics. FFT analysis enables applications like spectrum analyzers, audio spectrum visualizers, vibration analysis, and frequency domain filtering on microcontrollers. Microcontrollers handle encryption and secure communication by executing cryptographic algorithms to protect sensitive data and ensure secure data exchange between devices. Implementing encryption algorithms involves writing software routines to perform cryptographic operations such as encryption, decryption, authentication, and key management. By encrypting data using algorithms like Advanced Encryption Standard or Rivest-Shamirad-Altman, microcontrollers can secure communication channels and protect data from unauthorized access or tampering. Cryptographic libraries provide pre-written software routines and functions for implementing encryption, decryption, and cryptographic operations on microcontrollers. These libraries offer a range of cryptographic algorithms and protocols, including symmetric and asymmetric encryption, digital signatures, hash functions, and secure key exchange mechanisms. By using cryptographic libraries, developers can ensure the security and integrity of data in microcontroller-based systems. Microcontrollers support the development of secure IoT devices by implementing security features and protocols to protect against threats such as eavesdropping, data interception, and unauthorized access. Secure boot mechanisms verify the integrity and authenticity of firmware during boot up, ensuring that only trusted code is executed. Firmware update mechanisms enable secure over-the-air updates, allowing devices to receive and install firmware updates securely over a network connection. Secure communication applications using microcontrollers include encrypted messaging, secure data exchange, and secure access control systems. For example, microcontroller-based IoT devices can communicate securely with cloud servers using encrypted protocols like transport layer security or message queuing telemetry transport, ensuring data confidentiality and integrity during transmission. Similarly, microcontroller-based access control systems can authenticate users and grant access privileges securely using cryptographic protocols and secure communication channels. Microcontrollers handle power management and energy efficiency by implementing hardware features, software algorithms, and low power modes to minimize energy consumption in battery-powered applications. Optimizing power consumption involves reducing the energy usage of individual components, optimizing firmware execution, and leveraging low power modes to minimize idle power consumption by implementing power-saving techniques and efficient power management strategies. Developers can extend the battery life of microcontroller-based devices and improve overall energy efficiency. Low power modes in microcontroller-based systems are crucial for conserving energy and extending battery life. These modes allow microcontrollers to reduce their power consumption when idle or not actively processing tasks. By entering low power modes strategically, microcontrollers can minimize energy usage during periods of inactivity, which is essential for battery-powered devices that need to operate for extended periods without recharging. Microcontrollers support the development of energy-efficient applications through various means. They include implementing efficient algorithms, optimizing code execution, and leveraging hardware features like low power modes and sleep states. Developers can design applications to minimize unnecessary computations, prioritize energy-intensive tasks, and utilize power-saving techniques to maximize energy efficiency in microcontroller-based systems. Energy harvesting involves capturing and converting ambient energy from sources such as light, heat, vibration, or motion into electrical energy to power microcontroller-based devices. Microcontrollers can interface with energy harvesting modules, such as solar panels, thermoelectric generators, or piezoelectric sensors, to harvest energy from the environment and recharge batteries or power devices directly. Energy harvesting enables self-sustaining and autonomous operation of microcontroller-based systems in remote or energy-constrained environments. Low-power applications implemented with microcontroller. Microcontrollers in these applications are optimized for low-power operation, utilizing sleep modes, efficient algorithms, and energy-saving peripherals to minimize energy consumption and maximize battery life. Microcontrollers handle communication with other devices and systems using serial communication interfaces such as serial peripheral interface and inter-integrated circuit. Setting up communication involves configuring the microcontrollers, communication ports, defining communication parameters such as baud rate and data format, and implementing protocols for data exchange. These interfaces enable microcontrollers to communicate with sensors, actuators, displays, memory devices, and other microcontrollers in a system. Data storage and retrieval applications using microcontrollers encompass various scenarios, such as storing configuration settings, logging sensor data, or managing user preferences. For instance, in a weather monitoring system, a microcontroller may collect temperature and humidity data from sensors, store it in internal or external memory, and retrieve it for analysis or display purposes. Similarly, in a smart home application, a microcontroller can store user-defined schedules for controlling lights or appliances and retrieve them as needed to automate tasks. Microcontrollers handle signal processing and analysis by executing algorithms to manipulate and interpret analog or digital signals. For example, in a biomedical device, a microcontroller may process signals from sensors to detect physiological parameters such as heart rate or blood pressure. The microcontroller analyzes these signals using mathematical algorithms to extract relevant information for display or further processing. Implementing digital filters and algorithms with a microcontroller involves writing software code to perform specific signal processing tasks. This process includes defining filter characteristics, such as cutoff frequency or filter order, selecting appropriate algorithm, and optimizing code efficiency for execution on the microcontroller's hardware platform. Digital filters can remove noise, enhance signal clarity, or extract features from raw data for subsequent analysis or interpretation. DSP libraries provide pre-written code modules and functions for common signal processing tasks, such as filtering, convolution, or spectral analysis. These libraries simplify the development process by offering optimized algorithms and routines that can be integrated into microcontroller projects with minimal effort. DSP libraries abstract complex signal processing operations, allowing developers to focus on application-specific tasks rather than low-level implementation details. Microcontrollers support the development of projects involving audio processing by executing algorithms for tasks such as audio playback, recording, or manipulation. For instance, in a portable music player, a microcontroller may decode audio files, apply equalization or volume control, and output the processed audio signal to speakers or headphones. Similarly, in a voice-controlled device, a microcontroller may process audio inputs for speech recognition or synthesis. Signal processing applications using microcontrollers include audio processing, image processing, biomedical signal analysis, vibration analysis, and environmental monitoring, among others. These applications leverage microcontrollers' computational capabilities to analyze, filter, or manipulate signals from sensors, actuators, or external sources for various purposes, such as control, monitoring, or analysis. As we conclude today's exploration of microcontrollers, we hope you're inspired to embark on your own projects and explore the limitless possibilities this versatile technology has to offer. Don't forget to subscribe to Loops and Loops for more captivating content on electronics, programming, and DIY projects. Let's continue to loop in new knowledge, innovate with technology, and push the boundaries of what's possible with microcontrollers. Until next time, keep those loops tight, keep experimenting, and keep creating with microcontrollers. Thank you for joining us on this exhilarating journey.